Sir, welcome to the Applied Seminar. Welcome to our speaker, Michael Albergo from Harvard University.
Thank you. Thank you for having me. Kind of a easy trip for me now that
you're muted.
I'm muted. But this one shouldn't be muted. Right?
Okay.
Yeah, I muted myself because you get the feedback. I'm having an issue. This needs to be minimal. Stuck it down here. Okay. All right, good. Okay, right. So I'm Michael. I am a postdoc up at Harvard, and I research kind of topics at the intersection of applied math, scientific simulation, sort of geared toward problems in statistical physics. And today I'll tell you a little bit about work we've been doing related to dynamical transportive measure. And ways we're trying to apply this to understand generative modeling better in machine learning, and also devise new types of sampling algorithms, sort of in the context of where you have no data initially. Okay, so before I get any farther, this is how many more Zoom signs are there going to be? Hold on. Meeting is recorded. This can go away, and we can return. Okay, right. So this work is with a number of collaborators. The first half is going to focus on work done with Mark, Kyle, Nick, Rajesh, Eric, Jan, Saining, and Yifan. And then the second half will focus on work really done with Eric, but with an eye toward problems with this crew of folks up here for the study of the statistical physics problems in quantum field theory. Okay. And as a quick advertisement, and maybe not the best audience because there doesn't seem to be a ton of students in the room, but I'm starting a group in applied math at Harvard in 2026. So if you know any students or any postdocs who are interested on themes related to computation and the study of the natural sciences, definitely have them reach out. I'm looking forward to getting to meet some people. Okay. And in that theme of nature and computation, sort of the motivating framework for my work is to think about, the complex structure that we see in the world, both in sort of the social world, wherein we might, now want to be able to model, in the case of machine learning, like, aspects of human creativity, being able to associate language to the creation of videos that sort of define that language. For example, this surreal creation of a flower growing on a windowsill, or the aspects of intelligence related to human language, in which we learn from an abundance of data, right? We have, millions of samples of data for which we devise algorithms to learn from. And then at the same time, we have this sort of dual picture of the natural world for which we have many theories, but limited data to sort of express in simulation or in sort of experimental study, whether or not those theories are correct. Right. And so I'm interested in sort of the duality of these two problems in the sense of, how are the methods through which and in particular, I want to think about how generative models, which we've seen great success of recently in machine learning, can be applied in the context of thinking about scientific simulation. Okay. So we can frame what these dual problems are. Okay, the first is, broadly under the umbrella of, I'd like to estimate some unknown probability density function, which I'm going to call here rho 1, just to fix notation. Okay, and we can think about doing this from a variety of ways. In the social setting, as we were talking about, this might be, estimated through access to sample data, like images and videos and things like this, right? So we'd have access to images of the natural world that we're going to say are from rho 1, and we'd like to learn a model for rho 1. Or alternative, we have access to some energy function, say, a Hamiltonian, some Boltzmann distribution, something that describes a physical system, maybe the conformations of a molecule. And we'd like to learn to sample from that density exactly, or, in an unbiased fashion, so that we can, infer some sort of statistics about the system that we're trying to study. Okay. In particular, there's been an incredible amount of success in number one here through the ascendancy of generative modeling. Just as a quick sort of historical development over the past 10 years even, we've gone from the problem of sort of generating, for example, low dimensional MNIST digits, for example, trying to draw digits 0, 1, 2, 3, 4, 5, things like this, for which recently this sort of perspective has been associated with the Nobel Prize, to now being able to sort of at a whim query one of these large language models to tell me, draw me an image of two cartoon bears solving a chemistry problem, and you're able to get a representation of this pretty immediately. And what I think is kind of striking about this trajectory is that as these models have gotten better and better over time, with access to a lot more computer power, but as the methods have evolved, so too has sort of a manifestation of measure transport perspectives, building maps between distributions as the dominant features of the algorithms we use that are performing the best of these tasks. Okay. So what I want to talk about today are some new algorithms for this sort of dynamical transport of measure, so measure transport perspective on generative modeling. And I'll lay out what a picture of what that problem challenge is, and tell you a little bit about a paradigm my collaborators and I have been working on that we call stochastic interpolants, and some applications for them in machine learning. And then at the same time, I want to pivot back to this question about, the no data regime, where we learn from example, sort of constrained theoretical considerations about physical system, learn to sample. Okay, we're going to try to learn to sample from unnormalized densities better. And to do that, I'm going to use some perspectives from annealed importance sampling and some ideas in non-equilibrium thermodynamics, and talk about how we can augment these, conventional MCMC algorithms with some notion of measure transport, and then show some applications of doing that.
It's a kind of a bridge between these.
Yeah.
If you have a lot of data and you create a posterior distribution for parameters of a model, you would like to perhaps evolve the distribution from prior to posterior.
Yep.
So that puts you on the right side. How do I do that evolution?
Right.
How do I choose the right grid functions and so on?
Right.
But it's for a case with a lot of data.
Yeah,
But
totally.
it's not, it's not just
sampling.
It's not just sampling.
Right, yeah. So that's like in the ML context, I think they would call that learning an energy-based model,
Yeah.
right, in some sense. And then, the challenge they face there is how do you actually train that energy-based model? It's like kind of want to doing both of these simultaneously.
Yes.
Yeah, I actually think that's a hard problem. And one that I won't talk about today because I don't know how to solve it. But it's definitely related and sort of bridge between these two perspectives. Any other questions? Should I get one? Okay, the transport framework, just a fixed notation and sort of speak the same language while we think about this. So I like to think about measure transport as sort of the simple setup. I have a base distribution, which is something I know a lot about. I can sample it. I know, how to compute the likelihood underneath it, things like this. And what I would like to do is take that base density, which I call rho 0 here. Maybe it's a Gaussian. And I'd like to build some sort of reversible map that takes rho 0 and pushes it forward onto some rho 1. Okay, rho 1 is this target density we want to infer about. Okay. But of course, for most distributions of interest, we don't know what T is analytically, so we need to, discover it in some parametric class. And if we want this parametric T to be useful, well, one thing we might want to compute, for example, is a change of measure associated from rho 0 to rho 1 induced by T. And in that case, we need to be able to take some determinant of the Jacobian of this transformation. And so if there's structure on T, then this is going to be a lot more tractable than if this is some sort of dense operation. But at the same time, if you want T to be expressive, okay, you don't want to put too many constraints on this. So there's this balance that people have spent some time thinking about is how do I trade off tractability for expressivity? Okay. And as an incomplete and narrow history of how people have thought about this problem, at least for how neural networks got introduced to it and the like, I like to think about sort of this trajectory where people started saying, to solve this measure transport problem and like computationally, let's break down T as a sequence of smaller maps, okay, maybe each of these is a simpler function so I could represent it in a more constrained parametric class. So this is kind of the work of Chen and Gopinoff in 2000 with this paper called Gaussianization, and Eric Vandenadden and Asman Tabak and postdoc sort of extended this to sort of learn these maps sequentially in a, not with neural networks, but in, you know, a small parametric class. And then the neural network folks came along and said, what if each of these sub TK are actually parameterized by some big neural network? And what kind of mileage can we get out of that? So this is work by Laurent Din and Danilo Rezende, George Papamakarios' company. But an obvious question to sort of tie back to maybe how applied mathematicians have been thinking about this is, what if I take the k equals infinity limit here and I sort of imagine t as the solution of some continuous time flow? Okay, so, you know, applied mathematicians have been thinking about this for a while with, you know, McCann's displacement interpolation and sort of the Benamou-Brenier framework of optimal transport. But folks have also been recently thinking about, you know, endowing this continuous time transport with neural networks. Okay. And so I'll describe a little bit the language for doing that. We think about these maps in continuous time. I think it's, again, sort of to fix notation, but to bring home the point. Here we have a pictorial representation of some one-dimensional Gaussian that I'm calling here rho zero, and we're going to imagine a continuous deformation of this probability density to some rho one at time t equals 1. Okay, and what we would like to learn across this whole trajectory is a flow map that I call capital X sub t, which takes in some initial condition and tells you what the output should be along some deterministic flow lines, right, at time t, that sample is mapped to. So this is sort of the time-dependent map that brings me somewhere along this deterministic transport. And if you want to compute x, what you need is to learn some vector field or some drift. There's a velocity field that I call B here that is placed in this ODE. And xt is going to be endowed by solving this ordinary differential equation. Okay. But we could also ask, you know, this is at the level of individual samples and looking at their trajectories. What about, you know, the evolution of the density itself? So we know this density is going to solve a transport equation, which is basically just conservation of mass. You know, the time change in the density must sort of obey any sort of incremental inward or outward motion given by this divergence. Okay, and we would say that we have the rho t that solves this equation if given some initial condition at time t equals 0, it's equal to rho 0, but at time t equals 1, we've pushed the mass. Okay, the mass has been pushed. So when
you're thinking of that as an equation for rho.
For rho.
You could also think about it if you had a path in mind for rho.
Yeah, for B.
Equation for B.
Exactly. Yeah, yeah. I just only phrased it like this because I just talked about this sort of B perspective of P. But you're right. And in fact, if we fix rho, and there's some mild conditions on B, you know, it needs to be one-sided Lipschitz function, then we know that there's a B exists that allows us to fulfill this equation. And one open question we might have is, how do I actually find B, you know, between rho 0 and rho 1? And as you say, there's actually many rho t, for example, that would perform this connection. We need to choose one, and then we need to choose the B associated with that. Okay, and so what would be the kind of dream scenario for doing this learning? Is there like a very simple paradigm for learning B? Well, the best thing we could possibly ask for is that we have access to some B that we can query, and we perform regression on it over the time-dependent density that I need to know it. You know, for every rho t, I can compute what BT is and fit some models to it. Of course, this is like, as phrased, a total pipe dream, because if I have B, why am I bothering to learn for it? But nonetheless, I think it's still nice to think about this sort of regression. And the other issue is we haven't chosen a rho t to actually pick this expectation for. Right? There's many that would do it. We need to choose one, and then we would need to, you know, fit this quantity. So what I want to first talk about today is a way to basically do this by learning a velocity field everywhere over this interval, instead of relying on some sort of maximum likelihood estimator, you know, PDE solution. And the tool that we've been thinking about to do this, we call a stochastic interpolant. Okay, and so this interpolant function, which is sort of the meat of this idea, is a simple function. For example, 1 minus t x0 plus t x1. Okay, it's a function of t, x0, and x1 that has the boundary conditions that if I put in t equals 0 here, I should get back x0, and if I put in t equals 1, I should get x1. Okay, and x0 and x1 here are going to be drawn randomly from some sort of coupling. It could be an independent coupling where I draw an x0 and then I draw an x1, separate from each other. It could be some joint coupling in the case of like optimal transport. Maybe you have the optimal transport coupling and you want to use this to sample. But if you evaluate, sort of one of the important points is if you evaluate I, it's interpolant, drawing these x0 and x1, okay, from some coupling, which I call x0, x1, then I is actually a stochastic process which samples some time-dependent density rho t. It's some, we don't explicitly say which one, but there's a representation for it. You can express it as an expectation over this delta function, which isn't really a useful form, but it exists. And there are two knobs that affect what rho t are. The first is the choice of the interpolant. I wrote here a very simple linear interpolation, but you could imagine nonlinear functions that also maintain these boundary conditions. And the second is the choice of coupling. So for example, as we said, there's maybe this optimal transport coupling, maybe other structured couplings that relate your data in ways that could be useful. Okay, but a totally valid one is just product distribution. Okay, so this is what it would look like, for example, to draw from the interpolant. For the example I had pictorially drawn before, a single mode Gaussian to a mixture of 3 Gaussians over different times. So at each time slice here, I'm just drawing, 10,000 x0s, 10,000 x1s, and I'm computing the interpolant for these in sort of pictorial representation of what the density does.
These rows are overloaded, yes?
Rows
X0, X1 is drawn from some row of X1 and X0. It samples row of T comma X.
Or like I'm abusing notation.
Yeah,
Definitely abusing
Okay.
notation. Yeah, yeah.
okay.
These are separate densities.
Two different definitions of meanings of row.
Yeah, two
Got
different
it.
rows.
Got it.
And the only special rows I've labeled in the whole thing are the row 0 and the row 1 separately. But sure, yeah, you could call it something else entirely new or something instead of row. It's a totally different object.
And the
Got it.
interpolant density isn't as messy as it looks, because you could fix one of the variables. You could fix X and then write X0 and X1 in terms of X and one of those variables.
Yeah, exactly. Actually, there's a trick I'll show later on that allows you to do it. Yeah, exactly. It's a convolution. But it's not like interpolating densities themselves, right? It's this convolution. Like I could have an energy function e to the minus u0, and then one that's e to the minus u1, and do an interpolation of those. But that actually gives quite ugly transport ultimately. So this is like some nonlinear object that emerges through this convolution. Exactly. Okay, but if we've done this, we've checked off one box in our regression task in some sense, right? Now I have a row T that I can sample from to evaluate this loss. Okay. And I'll just sort of state as a proposition, but you can just sort of check by taking a time derivative of this guy and manipulating some equations, that in fact, the velocity field associated to this for the rho T that solves this transport equation has a closed form. And it's given as the conditional expectation of the time derivative of the interpolant condition that IT is equal to X. So what does this mean? We'll go back to this picture. Basically, if I wanted to know the velocity field B right here, I would look at all interpolating lines from the lines that I draw that cross through that point, right? Given that the interpolant is equal to X, and I would take the average of those points, and that would give me the flow. Okay. So that is nice in some sense, but also we don't know how to compute this in general, right? I could try to construct a Monte Carlo estimator for it, but in high dimensions, that won't work very well. So for example, if we plug in this definition for what the target velocity field is into this regression problem, a priori, this doesn't really help me solve my problem because I don't know how to compute this quantity and do the regression. But the Tower property of the conditional expectation says that when I take this expectation of this guy, this can actually just be evaluated by looking at what's inside here, which is the definition of the conditional expectation. So using that fact, we can write down a regression problem for B, which is that it's just the minimizer of this quadratic objective. It's just everywhere in expectation, these guys will be the same. Everywhere in expectation, just map B hat, some model, maybe parameterized by a neural network, to the time derivative of the interpolant, okay, over the coupling. Okay. So what's nice about doing something like this? Well, the loss is directly estimable. In the generative modeling sense, we usually have data from row 1 that we learned from. And if row 0 is a Gaussian, I can just draw those samples. This allows us to sort of build bridges between arbitrary densities if I have data from row 0 and row 1. And you can compute the likelihood of this by looking at the change of measure and using some, randomized linear algebra tricks to compute divergences and stuff like this in sort of efficient manner. Okay. And if we look at this loss, there's actually a way to bound what the Wasserstein distance is between what the true density should be and what my model is. Okay, this is Gromwell's inequality. It's not really a useful bound because it depends exponentially on the Lipschitz constant of a neural network, which we have almost no control over, but it's one you can write nonetheless. Okay, and then our generative model, the thing we would use to do our machine learning, right, is to say I have this V I learned, I solve this ODE, and I can produce this. Okay, so in the literature, some people this is also called flow matching, or rectified flows, from work from Aaron Lippman and Ricky Chen and Chung Wu. Okay, so for example, we could learn, this sort of deterministic transport between these weird densities, this is sort of moons and checkerboard densities that we might care about in 2D. But it turns out there's actually a simple set of criteria that relate the trajectories that you could get from a deterministic map to ones from some sort of stochastic diffusion, okay? For which the same time-dependent density is maintained for both of these processes. Okay, and the one thing we could ask is, are there any differentiating factors between learned transport that you get from a deterministic map and those that you get from a sort of stochastic map, Is one better than the other in some sense? How do you make this correspondence? The statement I'll make is basically that if you want stochastic transport, you need in your interpolating function any Gaussian random variable or any exponential family random variable. So say in this case, neither of these distributions are Gaussian, right? What I can do is take the interpolant I would usually use to construct samples from rho t and add onto it a Gaussian random variable that has the condition that at time t equals 0, and at time t equals 1, this term disappears, but there's like a Gaussian convolution everywhere in the middle of the interpolation.
That's the margin distribution. You could have whatever, you have a Gaussian process.
You could, yeah, there could be something much more
You get a
complicated.
rounding bridge taking you from 0 to 0.
Yeah. This is just like computationally the simplest one we can write down, so the loss functions are nice on the boundaries and stuff like this. But totally, it could be anything. Right. Okay. Then the same machinery that we just talked about can be used just like before. BT is now again the time derivative, the conditional expectation of the time derivative of the interpolant. But also, you can show that the score of this time-dependent density is equivalently described by a conditional expectation, where it's actually just the conditional expectation of this, essentially the noise that you're adding to this process, conditioned on xt is equal to x, with a prefactor that depends on the choice of the gamma t you use here. And again, if something looks like this and we can sample rho t, then there's a regression loss that we can write down for what this quantity is. Okay. So, if you have the score, we can augment the transport we were looking at before. First, we talked about a transport equation for which we had an ODE that we would discover the coefficients of, for example, B, by this regression procedure. But analogous to this is a Fokker-Planck equation, which is basically comes from adding epsilon times the score on both sides of the equation inside this div, that says there's a different drift, not B, but B plus or minus epsilon, some diffusion coefficient, times the score.
You did not define the score.
What's that?
You did not define the score.
Sorry, this expression here? Or
The meaning of score. It's
sorry.
gradient of the log of rho.
Totally. It's the gradient of the log of the time-dependent probability density. Thank you. I'm too deep into this to realize that I'm talking nonsense. Right. So if you have grad log rho, then you can write down an augmented drift that has associated to it some stochastic differential equation associated to this Fokker-Planck equation, where we would want to learn BF here, and the marginal distribution, time-dependent marginal distribution, the transport endowed by this ODE versus this SDE are going to be the same, but one is the diffusion and the one is.
Why do you call it that slash B? It's like forward back.
That is forward backward. Yeah. So, in some sense, here we said this thing is totally reversible. Here it's not totally formally reversible because there's randomization in it. So you can define a forward process You don't know where you'll end up because of the random motion, but it will be a sample from the distribution. This is not exactly reversible. There is a backward process that does the same thing.
Switches the sign. So
Switches the sign. Forward is plus, minus is backward, yeah. Okay, so it's okay, nice, I guess, that you could do this, but what is maybe something interesting about it? One is, we were motivated to try to unify these flow-based generative models and diffusion-based generative models. There's two perspectives in machine learning that are actually two sides of the same coin. It's kind of one thing we wanted to look at. But there's something else you could ask, which is like, which one is actually better if I've learned the same coefficients? Okay, so if we go back here, I'm basically learning the same coefficients. In this one, I could learn b hat. We know that intrinsically the score is part of that, but again, they're both just big neural networks that I would use for b hat and bf, right? What can we say about the transport? Okay, so here's one thing. If, we call rho hat the density that emerges from actually taking our model b hat, solving the ODE, looking at what the time-dependent density is at every, time up to time t, then it would satisfy some transport equation, right, associated to b hat. This is a different density from that target density, right? It's whatever we get from our model. If I wanted to ask what the KL divergence is between the density I get from my model and what the true density should be at rho 1, say if I had the real b and not b hat, and push forward this, then it turns out matching b hat to b is not sufficient to control the KL divergence between rho 1 and rho 1 hat. Okay, there's basically this term pops up that means you have to control the Fisher divergence, the differences in the scores. Okay. However, if you go through the same calculation, but use BF and get the rho hat associated with BF that satisfies this Fokker-Planck equation, then you'll find that you actually can bound the KL. So one application, go through the same thing and apply Young's inequality. You'll find that the difference in the drifts is enough to control this sort of distributional quantity that we care about. Okay, and it's going to depend on the diffusion coefficient you choose, and there's an optimal diffusion coefficient you could pull out. Okay, so this is one up. We've noticed that in practice this is true a little bit. It's pretty marginal, and in general, if you want to use these tools, solving an SDE is computationally more expensive than solving an ODE. And
but this shows the advantage of solving. This is the first time I've seen a quantification of which would be better in terms of the stiffness.
Yeah, I mean,
both available and what do I do?
Right, so you can write these down, how much they matter for you in practice when you put a neural network in here. You can get a signal, you can definitely tell, but you have to pay a lot more to solve the SDE than you do the ODE. I mean, maybe the number of function evaluations that you have to for the ODE is around 40. For this, it might be 200, 256. Depends on the diffusion coefficient you choose, but yeah, there is a slight difference. Okay, so what have we been using these for? I'm kind of interested in designing new tools that we can play around with. So one is just like, large scale generative modeling here, sort of demonstrating using these tools to generate images from the ImageNet database, or learned from the ImageNet database, but hopefully are not duplicates of them, when we would have cheated and memorized the data. But, analogous to what we've talked about is this notion of score-based diffusion, which you might have seen in the literature, which is basically learning a mapping from your data distribution to a Gaussian using the Ornstein-Uhlenbeck process. And that's one type of interpolant that you could write down, but when you have the sort of freedom to use various types of coupling between arbitrary densities, I could, for example, learn a map from my corrupted data to my clean data. So that's an example of this where we learn a map directly from this image that is corrupted to remove the corruption. Apply this to super resolution. There's ways you could write down the mathematics for this to solve like multi-marginal transport problems in some sort of dynamical sense. And lately we've been using it for probabilistic forecasting. So imagine my starting distribution is not something smooth, but it's a point mass, like the weather today. I know that it's sunny out and I'd like to know the ensemble of possible weathers that are going to come tomorrow. So here I'd like to learn a map in some dynamical sense from a point mass to a conditional distribution, conditioned on that current observation. So there are ways to write down this sort of stuff, and it connects to these things called former processes. In the 80s, now we're sort of trying to scale this up for large-scale weather simulation. Okay. So that was part one in the sense that we have all this data available to us. And we know now with these extremely fancy neural networks that people have designed as a community, we can scale these to high dimensional problems. But I think, I'm motivated more by like trying to figure out how to use these to solve scientific problems. It's very fun that we can draw images of lines and stuff like this, but it doesn't really keep me up at night, maybe the way some other stuff would. So I want to sort of ask, can we, take some of these concepts and apply them to the case where I don't have data to learn from? I need to bootstrap that up somehow, maybe some motivating examples I'll describe now. Right, okay. Sampling is an ubiquitous problem. If I have some energy function, U1, right, maybe I want to sample configurations of lattice descriptions of condensed matter systems, right? Could maybe study superconductivity or look at statistical physical theories of quantum field theories. Like here, I mean, this is just really an example of an Ising model, but we can make it more complicated. Molecular dynamics simulations, Bayesian inference, and gravitational wave astronomy, things like this, I think are very interesting and much harder problems. And so now we want to ask, how do we learn or infer what rho 1 is, given only query access to this guy and its gradient, right? Okay, so how do people usually do this? The first thing they might try is Markov chain Monte Carlo, where they try to build some structured randomized sequence of samples so that the expectation empirically of any test function H under this randomized procedure converges to the true expectation that we care about. And maybe one common tool that people would use to do this is Langevin dynamics, in which I initialize some walkers and I evolve them under the gradient of the potential plus some Brownian motion. And it's visualized here on this sort of multimodal distribution where the modes are pretty close together. Or alternatively, they may say, I don't want to simulate anything, but I have a very cheap surrogate model that I can sample. Right? So for example, rho hat here is my surrogate, which is a Gaussian, and I want to be able to compute expectations under this multimodal red distribution. Then what I can do is just reweight those samples in the expectation using importance sampling. This is effective when rho and rho hat have some overlapping support.
But if would you think that you're saying that the Langevin dynamics is an inappropriate tool for the multimodal cases because the distribution is not supposed to be visiting the valleys,
right?
While still satisfying these equations. So convergence can be slow.
Right, exactly.
So that's what's wrong with the use of the gradient of U. You need a different gradient.
Yeah, I mean, unless you ran it forever and ever,
Yes.
but there's going to be an exponential mixing time basically between these modes, and ergodicity in practice is basically
because you have to go through the valley.
you
You're
got
not supposed to be there.
right, and it may take you a while to even realize there is a valley, right?
Yeah.
If you have one mode that's totally isolated.
What are you doing in the valley? That's supposed to be an exponential likely event.
I don't want that in my expectation value. Exactly. Right. So exactly, if this is non-long concave, we can't really rely on these tools in practice. Especially if it's very long concave like this. And the same issue appears for different reasons in importance sampling, right? If I choose a surrogate model that has no overlap with these distributions, which would happen if I don't know where all the modes are, for example, then I get basically an exponentially high variance in my estimators that I would try to use. And in practice, I probably wouldn't trust it at all, because as you can see, I haven't even touched part of the cycle. Okay. So one thing people like to look at as a way of augmenting this, especially for the Langevin case, is to introduce some dynamics which anneal in this potential, right? Maybe I start with a higher temperature version of the multimodal one that I was looking at, and then over time, I anneal that temperature down to sample from the multimodal. Maybe I initialize a bunch of walkers that are exploring this. Okay, so the fixed notation, I would say here that we have some time-dependent potential UT. Maybe I'm linearly interpolating it between some simple U0 to some target U1. And in that case, we can just write down the PDF rho t as being the exponential of this time-dependent potential, plus I just tucked the log partition function into the exponent. Okay. What people want to do is then they say, I'm going to run these annealed Langevin dynamics, where this is now time-dependent potential. And at each time, I'm going to take a step of the Langevin, but I'm also going to change the potential to be the next time iterate in this process. And so, for example, if I started with this unimodal Gaussian and I had these walkers walking as the potential moved, well, okay, maybe they can move along with the potential in a way that allows them to capture the modes. There's various issues with this, but this is sort of the motivation. So what's happening here is the diffusion coefficient, which you can make a function of time, is setting the speed of the walkers, right? If it was infinitely large, they would always be mixing. But in that case, your time discretization would have to be infinitely small. So that's not really an option. And yeah, we can imagine this being some high temperature to low temperature multimodality. Okay, but the question is, what actually is the PDF of the solution of this SDE? Okay, so I'm calling it tilde for a reason. We can ask, does the solution x tilde have rho t, the target density we want, as its density? And the very leading question is no. Only if we took this diffusion infinitely high and made dt infinitely small, right? And that's basically saying I'm running a local algorithm at every time step and then giving it no time to mix. And so in practice, this would essentially result in the real density of this guy, rho tilde, lagging behind the target density. Okay, so how can we say it? Can we see this? We can read off what rho tilde is, right? By looking at its Fokker-Planck equation. So what do I have here? I have a drift term grad u that's going to appear in the Fokker-Planck as divergence of grad u times rho tilde. And then the diffusion term here is going to appear with the Laplacian of rho tilde. Okay, so that's what the Fokker-Planck equation is associated to the rho t endowed by dxt here. But we could just check by direct calculation that if I took the time derivative of the true rho t, I'm going to get this extra term here. Okay, that basically is a term related to how fast the potential is evolving. Okay, and then what I did here is I just added on 0 because we know grad rho t is equal to minus grad u rho t. Okay, so these guys are clearly different in the sense that if these terms are different, then this is an explanation for why these walkers are going to lag behind the actual density that we want to sample. So what would this look like in practice? Here's an extremely multimodal 40-mode Gaussian mixture, okay, where it's very spread out, you know, from like minus 40 to 40. If I initialize u0 as some Gaussian around, around 0, then these walkers would have to do a lot to get to these modes. And then the right here, you see in the background what the potential is evolving according to how the potential is evolving according to time, and what the associated Neil-Langevin dynamics walkers are doing. And as you can see, they're not keeping up with the potential at all. And this was for a diffusion coefficient of 4, but of course I could crank it up. There is now diffusion 15, that still lags behind, right? And I would really need to take the diffusion coefficient huge and the time step really small to be able to do this. So this is an issue. And in theory, it can be fixed with reweighting. And the way I think about this relates to a topic in thermodynamics called Jarzynski's equality. Okay. And so I'll state what that proposition is. Basically, if I kept track of a weight for each of these walkers, that I'm calling AT here, then I could look at the solution of a set of coupled equations for an xt and an AT, where x is my Langevin dynamics as I had before, and AT is keeping track of the time-dependent change in the potential. Okay? Then you can write down actually that if you want to compute the expectation for any test function h under your target density rho t, it's actually representable as path expectations for xt and a of the expectation of e to the AT, this is the weight, times h of x divided by the expectation of e to the AT. Okay? This is just like a continuous time description of annealed importance sampling. And I just wrote it down. You can prove it pretty straightforwardly. I mean, just looking at the joint Fokker-Planck equation for the joint PDF of x and a, and manipulating a few of the equations. Okay, but if you do this, it turns out that the ratio of the partition functions between rho t and rho 0 is actually just given by this path expectation. Okay, and the non-equilibrium thermodynamicists, the people who are studying how proteins would, transition between different states, would say, okay, here's the change in the free energy, and what this is giving me is the average work done in all the possible ways I could take that molecule and evolve it to its new state. Okay. In that case, I think it's a really kind of profound thing that Chris Jarzynski wrote down in the 90s. Here it's just importance weights. It's not like a physical, beautiful thing. Okay, but there's still an issue with this, right? In the sense that I'm just adding importance weights to a thing which is going to have very high variance, right? If we looked back at this simulation, you know, if this is my surrogate model and I'm trying to take expectation under that background contour plot, even if I have importance weights on this, the variance of my estimator is going to be gigantic. So, can we fix this somehow with measure transport is sort of the pitch. Okay. And again, we'll return to the flow map. There's a BT that we could learn between this rho 0 and rho 1. They're not inferred just by data now. We know it's e to the minus u and e to the minus u1, right? Again, there's a continuity equation. And there's also a Fokker-Planck equation. But because I know u, I can just write down this term that's equal to 0. Okay? This has the same rho t as a solution. Okay. So if I have discovered a BT that solves my transport, then I could just use this SDE directly, which is a Niels-Langevin dynamics term, plus a drift. This is my BT, plus the diffusion. And I would have the XT is from rho t if I could find the BT that this is associated to. Okay. So what if you don't have the perfect B? Okay. We could again look at the expression we had for what the Fokker-Planck equation was for this walker. Before we had dt rho t is equal to epsilon nabla dot grad u rho t plus grad rho t. Okay, that was the Fokker-Planck equation for our Niels-Langevin dynamics. And now what I'm saying is I'm adding on this drift term here. And then if I actually just expand what that equation is, I just add it onto the other side to say I've balanced my equations, right? And now this is the Fokker-Planck equation associated to this guy if I have the wrong BT. If I have the correct BT, all these terms are going to simplify. But if I have the wrong one, this is what the non-equilibrium system is that I'd be simplifying. So we could proceed the same way and say there's now a new non-equilibrium term in this Fokker-Planck equation. And the weights that I read off to do importance sampling can be achieved the exact same way, which is say, look at what the non-equilibrium term is. Keep track of those guys in terms of how they evolve with time. Those are the weights I would use to compute any expectation.
But wouldn't you have your modified drift in the XP equation?
I would, and that is a bad typo. Yeah, this should have this should have BTXT times DT in it. Definitely. So imagine I had written down the right equation. This would be true. Yes, thank you for catching that. If I evolved with B hat like this guy, with B hat, so yeah, then exactly these would be the associated weights that I need because you just proceed as before. There's a non-equilibrium term that pops up. Those should be weights. Okay, so now I could ask about how do I learn B? Even if I have a wrong B, I know I can still sample unbiasedly, but I'd really like to find the right, because if I find the right one, these weights will become 0. Okay. Right. This is just summarizing this again. This is correctable dynamical transport for sampling. And one thing to note is that epsilon of t could be any value here. And again, in the limit that epsilon of t is equal to infinity, we would again have perfect sampling regardless of the effective p. Right. So this is in some sense some sort of strict augmentation of the Niels-Langevin dynamics. Okay, how do we learn B? This is the equation we have, right? This is the Fokker-Planck equation we get for rho hat, right? For B hat, sorry. And we would know two things. We'd know we'd solve the transport if one of two things are true, right? One is that we satisfied the continuity equation or transport equation. That's the guy we had from before. And the other would be if we got rid of the non-equilibrium term, because then we're back to doing the normal sort of transport, normal sort of exact sampling we expect to be doing. So these are both avenues to learning some sort of math, right? We could either set this equal to 0, or we could set this equal to 0. If we look at the second one first, I would like an equation for which, I would like to find a B hat for which this is equal to 0. Well, I could just take that expression, square it, and learn the B hat everywhere for which this then would go to 0. Okay, right? Basically, what I want is these first three terms to be equal to the change in the free energy. Right? So this is basically a physics informed to neural network loss. I want this part of this physics equation to be true. It's a fluid dynamical equation. And so I just want to minimize this quantity over the support where I need to know what B is. Okay. So we would say that in this case, you parameterize B and you also parameterize a model of the free energy, FT. And the minimizers, B and F of this loss, are such that FT would actually be the free energy of this change in from rho 0 to rho 1, and BT would solve the transport. Ultimately, you don't need FT for anything else. It's just really a crutch here for the learning. It's not part of the sample. But it also is kind of nice to have an estimate of the free energy. Okay, and the sort of nice thing about this is valid for any choice of rho hat in this loss, right? It's a pin loss. I know it's 0 only when I've solved it everywhere in space. So the expectation I'm taking doesn't actually affect the minimizer, right? And in that sense, you know, to evaluate this, what I would have to do is walk out some walkers, right? With my model B hat, use those samples which are only approximately from the actual target one because I haven't learned yet, and then perform this minimization. But that's valid even if the samples are incorrect. That'll sort of bootstrap up in that way. There's an alternative perspective, which is to set this guy equal to 0. And if you do that, there's a loss that you can write down that's already in the literature called action matching. Okay. And you could sort of see that this is the case by realizing that this is the Euler-Lagrange equation for this if I set B hat equal to the gradient of some potential phi. Okay. This is a separate loss. This one I don't like as much because you actually need samples from OT. So you need to use your importance weights in the evaluation of this loss. And then the variance of the estimated is obviously going to be higher. Okay. So what happens if we learn B? Okay, here's an example. Here's what we had before when we were sampling this 40-mode Gaussian mixture and just using the annealed Blanchard dynamics. And here we're augmenting that with the learned B that we have. So as you see, it's like basically correcting for the lag in these walkers. So annealed Blanchard dynamics is doing some invariant thing on the time-dependent density. They're moving around on whatever it is, but also this is making sure that they actually end up in the right spot. So you could use this without any diffusion, and then you just have a flow map. And maybe that gets you to some ESS of like 95%. But if you turn the diffusion on, one thing we notice is that you always get a better performance. So this is another example of stochastic transport can seemingly just be better than deterministic if you want to pay for it. And so we really tried to push this in terms of like, seeing that fact. And so here what we did is we said, let's take another Gaussian mixture, but instead of it being in 2 dimensions, we'll push it to 36, 64, or 200, sort of like this, and see how the performance drops off using the exact same neural network. So not like increasing the parameters of the model. So here are some cross sections of what this mixture of Gaussians looks like. It's not a totally trivial density. And in this plot, basically at diffusion coefficient equals 0, this is the effective sample size we get from the algorithm for the different dimensional problems. Okay, just using transport alone because the diffusion coefficient is 0. So as you see, as the dimension grows, the effective sample size is going to drop off because it becomes harder and harder to learn the transport alone exactly as you increase the dimension, which we would sort of expect to be true. It's basically trying to match the right distribution everywhere. This is sort of an extensive quantity. Small errors are going to propagate more in high dimensions. But if you turn the diffusion coefficient on, you'll see that with the same learned model, all of these guys are going to start converging back to like near 95, 100% ESS. If you want to pay for more diffusion, the takeaway we're a little bit confused by here is that you actually get better performance with diffusion when you have transport than when you have no transport. If you have no transport, you really have to send this diffusion coefficient like gigantic to get out of the 0 ESS range. But here, a little diffusion helps more once you've learned a little bit. Okay. And so then we applied this a little bit to the study of a continuous version of the Ising model. This is what's known as a 5-4 theory in statistical physics, which is like a toy example of a magnet. So for certain parameters of this energy function related to this nominal mass term and a coupling constant lambda that tells you about how self-interacting this field is, this lattice will become magnetized. Okay, so it might take all negative values or all positive values, or there's a phase transition that you can approach for m squared and lambda, where these correlations begin to emerge, but they haven't become like totally positive or negative. And so simulating this phase transition is generally a hard problem for these types of algorithms because local Monte Carlo type things will fail to mix. Because what'll happen is if we look at the average magnetization of these lattices, after you go past the phase transition, you'll see that there's two wells. They're either negatively magnetized or positively, and learning sort of local algorithms or using local algorithms to sort of sample these multiple wells is difficult. And so we applied this to our case and sort of were able to show that compared to yield importance sampling, you can get like a 2 to sometimes 3 orders of magnitude efficiency neural network at the price of sticking a neural network into your sampling algorithm, which is of course more expensive than just computing the.
What, at the cost of what, speed or
Yeah, in the sense of like, if this is
memory?
some like multi-layer perceptron or feed-forward neural network, evaluating it at every step of your algorithm is more expensive than just having to evaluate, for example, the gradient of this function which is given to you.
Yeah, the cost is an area of training neural net, don't really know what you're gonna get.
Yeah, so I mean, never mind whatever you get, can you get like trade-offs, curves, you know, this is time for, you
Yeah,
know, whatever.
so that's one thing
Accuracy.
we're like trying to compute now, like basically a flops. Like if I
Yeah.
can pay this much in flops, how much is the cost of my algorithm grow with the dimension? In this case, the dimension is important because if you simulate this at the phase transition, you know, this is like the main knob, which makes the problem harder. So we're trying to write this down and do the experiment, but it's kind of hard to figure out what the best apples to apples comparison is because of, you know, if I really wanted, the lattice field theorists who want to study this will use like Aurora's supercomputer, you know, 120,000 GPUs simultaneously on a 10 to the 9 dimensional problem.
What is the dimension of your space here?
So this is in one space, one time dimension. So this is a 2D lattice.
Why use neural nets? Use some flexible basis or kernel or whatever.
Totally. This is for me, I communicate often with the lattice field theory community, and this is a toy model for the problems that they want to solve. So like a way to sort of get in the door with them is to say, have you shown it on the 5-4 model? And then they'll talk about the harder problem. The harder problem is the study of the strong force, in which the lattice is a 3 + 1 dimensional lattice, so 3 space dimensions in one time. And the values that these take are not scalar values on the lattice sites, but on the link of every lattice, there's an SU3 valued matrix. Okay. And then they want to simulate this in like 10 to the 10 dimensions. And then all the algorithms there become very complicated because it's multimodality.
I mean, the dichotomy there, you're in the lower dimension case, you remove this theory with kernel or
Totally.
projection-based regression methods.
Yeah.
And have a very clean theory of its success.
Yeah, totally. People have
But when you
solved
go
this.
higher dimensions, that's when you need some adaptation.
Yeah, exactly. And then what they do in the state of the art is they run very, very curated HMC algorithms where every single thing has been optimized. You know, the force calculations, things like this, and then they spent a lot of time doing this. Yeah, this was more to communicate to them that we might have something to play with.
Right, but the trade-off question is actually quite interesting, like you were saying, like we could always like push the epsilon t to infinity, right? And that, so we can always increase the amount of effort we spend, and we should, you know, at some point get a good, accurate
Right.
solution.
Yeah, the importance weights would be controlled.
Yeah, exactly, right, but so the question is then, okay, if you use the neural network approach, like given the same amount of computational budget,
Right,
what delivers the better accuracy?
right.
Yeah, I was gonna say your apples to apples comparison should be dollars.
Right,
Is it
exactly.
like
How much
Yeah.
does it cost?
Yeah,
Right.
exactly.
Yeah.
To,
But dollars to me was flops.
Or right,
Like,
exactly.
There
Like,
should
how
be the
many
same.
operations like do we have as a budget?
Floating point operations. I need to pay.
I was not being tongue in cheek, I literally meant dollars.
I mean, there it's like, who are you submitting the job to? Because if it's on
Yeah.
Google's cloud, they charge differently for if I had my own computer. I think electricity is what you really should be measuring. And that's what the lattice field theorists do because they,
I mean, it's completely valid, it is a resource,
yeah,
electricity is money.
totally. But yeah, I think you're right. There is something that you could measure. Just like doing it carefully is the hard part.
Yeah, yeah.
Okay, yeah, that's all I have. Thanks so much.
I wasn't understanding everything instantly.
Hmm.
Rather 20 years ago, I co-authored a paper titled Adaptive Annealing.
Okay,
And about half of what we did you went far beyond.
Yeah.
But half is in, so.
Okay,
I
cool.
had
Please send me the work.
motivations and so on.
Okay,
Taken it through.
yeah, so send me the paper. I'm happy to talk about it.
We'll talk.
There's like some things that I do want to figure out about this, which is, for example, how do you actually choose a better annealing path? Because this is still an issue. There's bad annealing paths for which learning the vector field, even if you learned it, it's not super useful. For example, in this case, if I took this type of annealing and I had to push a Gaussian from like -5 to 5. What would happen is at U0, there'd be no mass over here and there'd be a lot of mass over here. And as you turn T on, mass would teleport over here. But if I were to do this in some continuous time way under some flow, then the vector field at some point here, B,